Physics 30s, Mr. Thompson here. All right. We're looking at Spectra and the Bohr model, page 114, unit 5 of the workbook. Emission and absorption spectra, the three types of spectra. So we're looking at continuous, emission, and absorption. All right, starting with continuous spectra. We have a heated material. So heated solids, liquids, and dense gases emit light with a continuous spectrum. So a hot object, glowing tungsten filament here for the light bulb, shines through a prism. The light refracts, okay, different wavelengths refract to different amounts, and it makes this red to violet or Roy-G-Biv spectrum. It's continuous, there's no gaps in it. The spectrum contains all frequencies, colors, no gaps. EMR is due to collisions between atoms. So EMR photons strike these electrons, atomic electrons, and excite them to higher orbital states, and then they fall back down and emit this light of given frequencies, okay? Of course, with all these different transitions that occur, there's a continuous spectrum, so all different frequencies. So emission spectra. So a low pressure or rarefied gas exposed to high voltage gives off specific colors, like a neon sign. So the spectra show a discrete number of bright bands. And so when you pass this low pressure excited gas, okay, in this case it's hydrogen, through a prism, you end up it's spreading out into red to violet, but only certain characteristic frequencies are represented. There are these gaps in between. Okay, so only really 4 main frequencies are given off in this example for hydrogen. Okay, let's take a look at an example of both of these. So if we look at the continuous spectra, we're looking at, of course, a device here. We use, instead of a prism, we use a spectroscope here in the school. And so light passes through a narrow slit here. And then, of course, you observe it through this part right here. Okay, and essentially it diffracts the light rather than refracts. But either way, it produces that spectrum. And so if you take a look here, here's an incandescent light bulb, right? Nice and bright light there. I hope you like that. Obviously, the glowing filament makes a white light. So it's essentially all the colors of the spectrum which blend together to make white. Now, how about the emission spectrum? Well, the emission spectrum can be observed with a gas discharge tube. I've got one right here. I'm going to put it on my lap. Hopefully I won't get shocked here or anything like that. It might be a little bit of a wild video. And this is neon light. Okay? Electrons are coming from the cathode to the anode and through this low pressure gas. And it's emitting light of characteristic frequencies. Not all frequencies are represented. It's not white light. Okay? All right, the third type that we want to look at is what we call absorption spectra. Okay? But to finish this one off, it says emitted EMR is due to the excited atoms themselves, and each atom has a unique emission spectrum, spectral signature, and classical theory could not explain why most frequencies are missing. But for the absorption spectra, when white light passes through unexcited gas, there are dark lines or missing frequencies in the spectrum. And so now you have a hot object, so emitting a continuous spectrum passing through an unexcited hydrogen gas, and the gas is pulling out some specific wavelengths that correspond to its emission spectrum if it was excited. And then when it passes through a prism, it ends up with a continuous spectrum with these dark bands in it. They're, of course, represented by light here because the dark bands obviously are gaps. It's where it's missing. So it says a gas absorbs the same frequencies of EMR that it emits. All right, let's look at some practice questions on this. So if we look, it says identify the type of spectrum associated with each of the following descriptions. So a low pressure neon gas is excited by current and gives off light. Well, like my example here with the neon light, it should be an emission spectrum. It's excited by current and gives off those characteristic wavelengths. A light from the sun after it goes through its relatively cold atmosphere. Oh my gosh, the atmosphere of the sun is still very warm, at least 5,000 Kelvin. And so in this case here, it should be an absorption spectrum because some of those wavelengths are being picked up by the cold atmosphere of the sun from where it is a continuous spectrum from the core. The light emitted from a hot metal, hot glowing solid, should be a continuous spectrum. Entire spectrum of colors are present, but there are a few dark lines, absorption spectrum. All frequencies are present, continuous, and there are a few bright lines, but the rest are missing. Those missing spots, right? Obviously, that has to be these big gaps between bright lines, so it's an emission spectrum again. All right, let's take a look and see if we can do a little bit of a puzzle solving or problem solving here. So if we look at this problem on emission spectra for 4 common elements, we want to figure out the gases in the samples below based on the spectrum. So if we take a look here, what we want to do is we want to see which ones are represented. Well, so first of all, I look for like these double bands that are shown here and here, right? And then I want to see, right, what else is represented here. And so if I look on this first one here, you can see that there's this double band. And then is there anything else that's kind of represented on there? Well, it seems to me that there's this set of 4 bands that correspond that are just like this right here. So it's got a double band, okay? And it has these 4. It also seems to have this one right here, okay? And one at the beginning. And so it looks to me like it's sodium and helium. How about the second one? Second one here, you want to make sure, I just want to see if we have it on the bottom there. Yeah, see there's a little band on the end of this one. So that definitely has to be mercury. But what else would be in there? What about hydrogen? Okay, so hydrogen and mercury. And then the third one. Okay, this one here, it looks like it has these two, okay, together, which makes the front part of it. Get rid of that so I can see it. There we go. And then you have to have at least something else in here. So looks like sodium might be involved. Unless it has all these bands for mercury. No band on the end. So probably hydrogen, sodium, and helium. Okay? And of course you can check your answers at the bottom.